Okay, so we've got postsynaptic potentials. Oops. All right. And so here we're looking at the difference between an IPSP and an EPSP. So an EPSP, we said, is an excitatory change in the membrane potential, right? So we're going to pretty much depolarize the membrane potential. And that, we said, could be brought about by the influx of ions like sodium or calcium, right? They're positively charged ions. When they rush into the cell, according to their ECDF, that generates a positive membrane potential change, okay? We can compare that to IPSPs, which pretty much hyperpolarize the membrane potential. Which we said is the flux of potassium or chloride, because potassium has an outward ECDF, although it's positively charged, and because chloride also has an inward ECDF, we generate more of a negative environment inside the cell, and so that is going to be a negative membrane potential change. And so let's consider two neurons here. So we've got a first neuron, this is our presynaptic neuron. Okay. We've got a second neuron that's being synapsed here. And so we want to be thinking about this first neuron as one synapse, but also think that there are many other synapses coming in on this neuron, right? Let's say we have two positive synapses, but then we have two negative synapses as well, okay? This is all going to be assessed at the axon hillock. This is the importance of IPSPs versus EPSPs. So this is the axon hillock where all of that is going to be assessed, okay? And so IPSPs are positive membrane potential changes. We want to be thinking about opening sodium or calcium channels, but we also want to consider that if we close the opposite channel, right? If we close potassium or chloride channel, we can also generate an EPSP. And if we close a sodium or calcium channel, we will also generate an IPSP, okay? So we also want to be thinking about the reverse type of synapse on this second neuron. And so this transfer of energy here, we call this synaptic transmission. Because the electrical energy from the action potential on this neuron, remember we have the action potential moving down the axon of this neuron, it gets to the axon terminal, we determine, but we open up calcium channels, we release that neurotransmitter, it binds to receptors over here, and we said depending on whether or not this was a sodium channel or a calcium channel, that would determine if it's an IPSP or an EPSP. Okay, and so that would also be assessed on the subsequent neuron at the axon hillock. And if we get to threshold, we would once again propagate an action potential down this neuron. And this is how this becomes the cyclical process of action potentials, neurotransmitter, action potentials, neurotransmitter, et cetera, et cetera. I also want to talk here a little bit about neural integration. And please excuse my scratchy handwriting today, or in general. So neural integration is basically this process where we integrate IPSPs and EPSPs. And when we say integrate, we really mean summation, there's frequency coding, there's divergence versus convergence. All of that information is kind of taken into account, and we determine if we get to threshold. So integrate IPSPs and EPSPs at the axon hillock. and determine if threshold is met. And if we meet that threshold requirement, then we generate a subsequent action potential, okay? Now I got another question here. Let me open this up. So someone's asking if neurotransmitters or if neurons go through all the trouble of sending action potentials, why would they release inhibitory neurotransmitters? And that's a good question. So in some instances, we want it to be harder to fire an action potential. One of those instances is immediately after one action potential, but also when we look at the muscle system, for example, there's going to be times when we don't want muscle to move, okay? So there will be positive changes that will generate action potentials or move muscle, as we'll see, but there will also be negative changes that will prevent or negate any movement. And so we want to be thinking about this in the types of signals that are sent in the nervous system. So we can have changes that make it more favorable to fire an action potential, or changes that make it harder to fire an action potential. And both of those types of responses are needed depending on different systems. We'll talk about examples in the muscles, examples in the cardiovascular system and cardiac muscle, as well as examples in the autonomic nervous system. There are times when we want it to be harder to fire an action potential. For example, when we want the heart to relax, or we want to slow down the heart rate, right? We want to make it harder to fire an action potential, harder to speed up the conduction of the heart. And so there are instances when we want that will be a favorable outcome, if you will, okay? So that was an excellent question. So there are times when making it harder for an action potential is the desired outcome. Any other questions on IPSPs versus EPSPs, on neural integration? So this is really kind of bringing everything that we've been talking about together. Okay, excellent.